Okay, we're happy for our last MOPA seminar of the semester to have Leszek Kołodziejczyk from Warsaw to speak on models of fragments of PA with low Scott rank. Go ahead, Leszek.
Thanks a lot, Arthur. I'm filled with some apprehension about this talk because it's on a topic that I really know little about, and it just so happened that I was asked a question or two, and I was able to contribute some answers. But the background knowledge given for this is not really the kind of background knowledge I have, although I'll try to mention the basics. So this is joint work. Very much work in progress, although I'll talk mostly about results that we already have. Joined with Mateusz and with Patryk Szlufik, who is Mateusz's PhD student. And it's going to be about Scott rank. I'll say in a moment what that is for those of you who might not know what that is, as I did not up to, I don't know, 2 years ago or something of that kind. But it will be about models of arithmetic, perhaps not piano arithmetic, but fragments. So that's the connection to this seminar. Okay, so I presume most of you know this language, mathematical object, whatever you want to call it. One can loosely call it a logic, the infinitary logic L omega 1 omega, right? So that's just an extension of first order logic where you allow countable conjunctions and countable disjunctions of formulas. Typically, you want to restrict yourself to formulas with a finite amount of free variables. So before taking a countable conjunction of formulas, you want to make sure that all of your formulas only talk about a fixed finite tuple of free variables. But that's a technical detail from the point of view of this talk. And probably the most famous result about this logic, that's the result that would come to my mind if asked, is Scott's isomorphism theorem from the 1960s, which says that given any countable structure, say A, you can characterize it up to isomorphism by an L omega 1 omega sentence, let's call it psi of A, isomorphism within the realm of countable structures. So you can distinguish it from all non-isomorphic countable structures. So you will not be able to distinguish your structure A from some uncountable structures in general. So any sentence that has this property, among countable structures, it characterizes a given structure A up to isomorphism is called a Scott sentence for A. And well, you can, as expected, you can define some sort of notion of syntactic complexity of L omega 1 omega formulas. And using that, you can talk about the smallest complexity needed to characterize a structure as a sort of measure of how complex the structure is. Okay, so as mentioned, within L omega 1 omega, you can stratify the formulas in a natural quantifier alternation hierarchy, namely sigma. I don't know how you pronounce this actually. Sigma in 0, well, infinitary sigma 0. The in stands for infinity, definitely. Infinitary sigma 0 and infinitary pi 0 is just quantifier free first order formulas. So that's a very, very weak class. And then at levels above 0, infinitary pi alpha is a family of is the family of formulas that are countable conjunctions of formulas that arise from taking infinitary sigma beta for beta smaller than alpha formulas and possibly closing them under universal quantifiers. So you get say level omega of this hierarchy by allowing countable conjunctions of formulas at finite levels, where the level may depend on the formula, of course. So it might be a sigma 1 formula and a sigma 2 formula and a sigma 3 formula and so on.
Leszek, so
yes.
I remember I was getting confused about this in some previous talks as well. So if you just look at the arithmetic hierarchy,
Yes.
Not the infinitary one. So if you have, say, sigma 1 arithmetic formulas, they would be at the sigma in 1 class?
They would be in, well,
Right,
yes and no. It
Oh, I
depends
see.
on whether you have something like the Matiasevich theorem available.
Oh,
So, so syntactically, no. An arithmetical sigma 1 formula will contain a delta 0 part. And, just from a legalistic point of view, that's not a sigma 1 infinitary formula.
right, because of the bounded quantifiers. But what about
Yes.
E1 formulas?
Yeah, but E1 are definitely infinitary sigma 1. That's right.
Okay, all right.
And
So
this issue of, sigma 1 in fact being E1 up to equivalence will come up, okay?
all right, thanks.
As a minor matter, but it will come up. And yeah, the infinitary sigma alpha for alpha greater than 0 is the dual class to infinitary pi alpha. So it's disjunctions of, existential closures of infinitary pi beta formula where the betas have to be below alpha, okay? So it's very easy to show that this hierarchy has omega 1 levels, so it's not exhausted at any fixed countable level. And you can use it once you have a notion of, formula complexity or rank, you can use it to, in combination with Scott's isomorphism theorem, to define a notion of rank for structures, for countable structures. This particular variant is due to Montalban. It was introduced about 10 years ago, and it's very robust. The advantage of it is that it has a number of equivalent characterizations. I will mention some later on. So Scott rank a la Montalban of a structure A, a countable structure, is the smallest alpha such that the structure has a pi alpha plus 1 Scott sentence. There is an IN missing in the superscript. So I do mean an infinitary pi alpha plus 1 formula, okay? Or sentence. So it's how complex a formula or sentence do you need to characterize the countable structure up to isomorphism among countable structures, okay? So yeah, if you have any questions, please do ask.
This might be somewhat silly, but why is there off by 1?
I will give you a result, an equivalence in a while that I think kind of explains this.
Okay.
That gives just at least some justification for that. In particular, I'm pretty sure that there is no structure with a pi 0 Scott sentence, is there? Can't be. No, you can't be. I mean, any extension of a structure.
Makes sense.
So if you didn't have the plus 1, then definitely you would be, missing level 0 for the first thing. But there are other reasons as well. So people study this quite a lot. So, for example, a well understood class of structures in this respect is linear orders. It's known that there are linear orders of all possible Scott ranks, starting at 1 maybe. Not sure about 0. Well, I guess the 1-point structure has rank 0. But a while ago, just a few years ago, people got interested in the Scott rank of models of arithmetic. This got pioneered by a paper of Montalban and his student, Dina Rossiger. I think the archive preprint is from 22. The online JSL paper is from last year. And they considered models of PA. It's sort of easy to see that the standard model has rank 1. You just list the diagram, the multiplication table, and you say that every element is either 0 or 1 or 1 plus 1 or 1 plus 1 plus 1, whatever. That's a pi 2 infinitary formula. But they also proved, this is just an observation, but they proved non-trivial results. For instance, they showed that every non-standard model of PA has Scott rank at least omega. So there are no non-trivial examples of finite ranks among the models of PA. And in fact, the so-called Scott spectrum of PA, meaning the set of Scott ranks of its models, is exactly 1 union the interval from omega to omega 1. So every infinite countable ordinal is the Scott rank of some model of PA. And an easy example of non-standard models of rank exactly omega that they provided is pointwise definable models.
But Leszek, but again,
Yes.
here something comes up. But all those ranks, they're of the form alpha plus 1, so they're all successors.
No. So.
Oh, I see. No. I see. The sentence is.
Yeah,
right,
that's a subtle thing. So they also study things like Scott sentence complexity, and this is a good example. So if a structure has Scott rank exactly omega, its Scott sentence, it might have a pi omega Scott sentence, or it might not. It's enough to have a pi omega plus 1 Scott sentence to I think it's possible to have a pi omega Scott sentence. I mean, yeah, I guess it is. I guess it is. Or am I wrong about this? Well, anyhow, the Scott rank doesn't fully determine the exact complexity of the simplest sentence that's a Scott sentence for a structure. You might have, you might have a sentence in the corresponding, sigma class, or you might not. So, so yeah, right. I guess that the natural Scott sentence for pointwise definable models is you just say that, well, each element is either defined by this or defined by that or defined by this and so on. Plus you state the theory of the structure. So that's pi omega plus 1. So possibly something is maybe pi omega sentences don't do the job, but actually I'm not sure. So Montalban and Rossiger, they asked whether any other models of PA have rank exactly omega, namely, are there non-pointwise definable models that have rank omega? And this was answered in the negative by Mateusz Wełek and by Patryk Szlufik. It's written up in Szlufik's master's thesis. And I think it's going to be part of a published paper that they will have co-authors on. David Gonzalez and Dina Rossiger, I believe. So that, I mean, once you have some understanding of the Scott ranks of models of PA, then a pretty natural question, at least in some circles, certainly for me, but I think Mateusz and Patrick had the same question themselves. It just occurs naturally to some select few people, is what about Scott ranks of fragments of PA, right? So what can the theories I sigma n or B sigma n offer that PA can't in this respect? So just as a reminder, I expect that the audience of this seminar knows this stuff, but I do want to remind you of it. If you have a model of, say, I delta 0 plus, let's have the exponential function most of the time, that's not a model of PA, then it has one of two flavors. Either it's a model of sigma n induction, but not sigma n plus 1 collection for some n greater or equal to 0. That kind of model that satisfies induction but not the next collection is sometimes called an I model. And a classical example of this is you take a model of a sufficient amount of induction, say sigma n plus 1 induction will certainly do the job. You could do less, but you will need at least sigma n plus the exponential function in case n equals 0. And you, let's call that model A, and you take its sigma n plus 1 definable elements. So elements that can be defined by sigma n plus 1 formulas without any parameters. In reasonable cases, that's never an initial segment of the structure A that you started with, unless it's the standard segment. So it's indicated by these blue things here. It's usually called K with the appropriate index of it should be A, right? There's no M here in this example. Sorry, that's another typo. And that's a typical example of a model of I and not B for at the right level. So the other kind of model that satisfies some arithmetic but not all is when you have a model of n+1 collection but not n+1 induction, again for some n greater or equal to 0. And the classical example is, again, you take the sigma n+1 definables of a structure satisfying enough induction. But instead of taking just them, you close them downwards. You take the initial segment generated by the sigma n+1 definables. This is sometimes denoted I n+1 of A, but I felt that it would get mixed up with the I model, so I'm calling these initial segments J. So K n+1 is sigma n+1 definables. J n+1 is the initial segment generated by the sigma n+1 definables. Okay, and something that well, for example, I wanted to understand, and Mateusz and Patrick certainly did as well, and I think it's a very natural question, is what are the bounds, in particular the lower bound? That was at least my main interest at the start, and this will be the main subject of this topic. What must be how low can the Scott rank of a model of I and not B, or of B and not I be, assuming, well, that will always be a non-standard model. So how low can you go? Presumably you can go below omega, but what is the bound exactly? And in that context, what happens to these classical examples, the sigma n+1 definables and the initial segments generated by the sigma n+1 definables? So here's our result. First of all, we have a lower bound. Namely, if you have a model of sigma n collection, where n has to be at least 1 for this to make sense. Sigma 0 collection is just sigma 1 collection. So if you have a model of sigma n collection, that's a non-standard model. I mean, the standard model has Scott rank 1. Then its Scott rank has to be at least n+1. Moreover, this bound is tight. I spent some effort trying to get the indices in these two later parts of the statement right, so I hope they're correct. So the canonical example of a model of I sigma n, namely the pointwise sigma n+1 definable model, that has Scott rank n+1, assuming it's a non-standard structure. And the canonical example of a model of B sigma n, namely the initial segment generated by the sigma n definables, that also has Scott rank n+1. So the jumps in terms of the required rank of a Scott sentence occur at collection, not at induction. And the lower bound here is tight. So, and actually the classical structures, the classical examples, the Paris-Kirby examples, provide the upper bound, the corresponding upper bound. So,
Leszek,
yes.
sorry for interrupting so much, but when I look at this, suppose A now is a model of PA.
Yes.
Is there some kind of a limit process that you could use these results to gauge the Scott rank for A?
That A is a model of PA.
Right. So it will be the union of all those things.
Yeah. So I would say that, well, actually, you get a proof. If you look at my statement A, then it actually implies directly. So this gives it's not a very deep fact, I think. So just proving that models of PA have rank at least omega. I mean, non-standard models. It's not very hard, although it requires some ideas. It's maybe not very surprising that you get a reproof by these means, because the proof here involves a hierarchical version of something that Montalban and Rossiger had. So it's not a big surprise. And I mean, the pointwise definables, they pretty obviously provide an example of Scott rank omega. So in terms of, least possible Scott rank of a non-standard model of PA, it is just, part A of the theorem plus, obvious stuff about
All right.
pointwise definable models.
All right, thanks.
So maybe just to reiterate, the jumps in required Scott rank for fragments of PA occur at collection axioms. So models of I delta 0 must have at least rank 1. They can't have rank 0. And in fact, the pointwise sigma 1 definable models will have exactly rank 1. And then models of B sigma 1 and also of I sigma 1 may have rank 2, but they must have at least rank 2. And then models of B sigma 2 and of I sigma 2 must have at least rank 3, and they might have exactly rank 3, and so on. And the least possible Scott ranks are actually exemplified by the classical I models and B models. Okay, so I will want to spend almost essentially the rest of the seminar of my talk giving you some ideas of the proofs. The proofs on the whole are not very hard, though with the exception of the pointwise definable case, they're not trivial. So parts A and C are not completely trivial. And what I'll do is I'll first prove the upper bounds, meaning the exact characterizations of how the classical models behave in terms of Scott rank, assuming the lower bound, and then towards the end I will say something about the lower bound. Okay, that's the plan for the remainder of the hour.
I just have a question about the last slide. When you say it may
is that the last slide?
Yes, thank you.
Yes.
A model of I delta 0 may have. That means there exists models of I delta 0 such that.
Yeah, and the natural example, which is in fact an obvious example once you see the next slide, is any pointwise sigma 1 definable model of I delta 0. But you cannot have rank 0 for some sort of pretty trivial reasons. It just so for example, rank 0 would mean a pi 1 Scott sentence. So pi 1 Scott sentences, even infinitary pi 1. So for example, any sentence any structure that satisfies the pi 1, the usual pi 1 theory of your model, will satisfy the infinitary pi 1 theory of your model, just because of how these hierarchies are set up at level 1. So yeah, rank 0 is some sort of very, very trivial notion. Okay, so here's a basic tool that was also one of the reasons behind Montalban proposing this specific notion of Scott rank. So what he proved is if you've got a countable structure A and you've got an alpha, it should be a non-zero alpha. One of the implications doesn't work for alpha equals 0, but it should be a non-zero countable ordinal alpha. Then having Scott rank at most A, most alpha, sorry, which is equivalent to, which is by definition having this pi alpha plus 1 Scott sentence, is exactly equivalent to a bound on the complexity of definition of automorphisms or automorphism orbits in the structure. So you have a pi alpha plus 1 Scott sentence exactly if every automorphism orbit of a finite tuple in the structure is infinitary sigma alpha definable without parameters. Okay, so that's why this particular notion is so neat. It's exactly about complexity of definitions of automorphism orbits. And I would say that this justifies the +1 in the official definition, right? That here in the bound on the complexity of definitions of orbits, you no longer have the +1. It's just a straight alpha. So one way of proving bounds on Scott rank of a structure is providing definitions of all automorphism orbits. Of tuples, though, of course, in arithmetic, we may care just about elements if we want to, because of the pairing function. Well, and proving bounds in the other direction is about showing that orbits can't be defined in a simpler way than what is required. This notion of Scott rank has many other equivalent characterizations. For example, the Scott rank of a structure is at most alpha if the set of isomorphic copies of alpha coded in omega in the natural way is pi 0 alpha plus 1 as a Borel set, sorry. So that's a descriptive set theoretic characterization. There is also a characterization in terms of how complex, in terms of computability theory, must finding an isomorphism between two copies of the structure be. And there are a number of other more combinatorial characterizations. So this is really a very robust notion, Scott rank. All right, so yeah, this is the tool we'll be using. We'll be mostly talking about automorphism orbits from now on. And let me first prove the simplest of the three parts of the theorem, namely that pointwise sigma n plus 1 definable models of I sigma n have Scott rank exactly n plus 1. So the fact that they have rank at least n plus 1, that's the lower bound theorem, and that will be proved later, so that we'll just assume that. Right, and here's another typo. This should be a less than. So we're left with proving that the Scott rank of a pointwise sigma n plus 1 definable model is at most n plus 1. And by the characterization from the previous slide, this comes down to showing that automorphism orbits are all infinitary sigma n plus 1 definable. But in the pointwise definable models, automorphism orbits are simply singletons because each element is definable and each tuple is definable without parameters. Since we're in a sigma n plus 1 definable model, each singleton, thus each orbit is, in the usual arithmetical sense, sigma n plus 1 definable. But we have n at least 0, so n plus 1 is at least 1. We have the exponential function, so we have access to the Matiasevich theorem, and therefore we can rewrite a sigma n plus 1 formula as an E n plus 1 formula, so no bounded quantifier part after the n plus 1 blocks. And that already counts as an infinitary sigma n plus 1 formula. So that's it, okay? Does this make sense?
Yes.
Great. Yeah, this was supposed to be the simple example. So now let's do B models, the classical kind of B models, namely initial segments generated by definables. I won't sketch, give you a detailed sketch at least of a proof for the completely general case, but I'll prove a simpler case and make some comments about how this is generalized. So recall, our aim here is that if you have a model of at least sigma n induction, say A, and if you take its sigma n definables and close downwards, getting Jn of A, that's a typical model of B sigma n and null I sigma n. And you want to prove that the Scott rank of this Jn of A is at least n plus 1. It's exactly n plus 1. And again, right, this is just copy and pasted from the previous slide. So again, the lower bound, that it has to be at least n plus 1, is provided by the general lower bound result, and we'll come to that in a while. On the other hand, the upper bound we have to prove so that it's no more than n plus 1 by defining automorphism orbits. That's what we have to do. We need infinitary sigma n plus 1 definitions of automorphism orbits. The definitions of orbits have to be without parameters. I might have not emphasized this. enough. So we'll make sure we're getting parameter-free definitions. And we'll study a simpler case. So we'll assume in addition, and for this we don't even have to assume that this model came from some end extension A, from a longer structure. We'll assume in addition that we're looking at a model of b sigma n plus the exponential function, in which the natural numbers are a counterexample. The standard cut is a counterexample to I sigma n. So we want the standard cut to be sigma undefinable, and the definition should be parameter free. Okay. Then immediately you have cofinal sigma undefinable elements, but this is not a general case. You don't always have sigma undefinability of the naturals in a model of the form J and of A. Okay, so this is the sort of model we're looking at. Okay, it's a model. By the way, I'm keeping X here just to indicate that we want to have it. I'm explicitly writing it down, but the proof for n equals 1 is much simpler than the general one, and you can actually avoid exp in that proof. So this result is not about the exponential function and the power of the coding power it provides. It's more general than that. So we've got a model J that satisfies sigma in collection, and that has a sigma in definition of the standard cut, which means that there is some delta indefinable set of type omega, of order type omega, you could call it. So you can enumerate it in increasing order as A0, A1, A2, A3, and so on. And this set is cofinal in the whole model in J. So that's exactly what being a model of B sigma n with a sigma n definition of the standard cut is about. We want to define automorphism orbits, so we need to understand automorphisms. And in general, this is known in large part thanks to work of Roman from almost 35 years ago, in fact. That in contrast to the sigma n plus 1 definable models where you have no automorphisms at all, models of collection and not induction, B models always have lots of automorphisms. And in particular, in this case, you can read this off one of the proofs of the existence of many automorphisms of a B model, that for tuples in such a model in which we have a sigma in definition of the standard cut, you can characterize being in the same automorphism orbit in the following pretty simple way. So two tuples, say R and S, are in the same automorphism orbit if and only if they satisfy the exact same delta zero formulas, and here I mean standard formulas, with parameters from this cofinal set of type omega, cofinal delta and definable set of type omega. Okay, so that's just how automorphisms of these structures work. If you satisfy this, which is clearly a necessary condition for being in the same orbit, because these AKs are all parameter-free definable, then this is actually enough to be connected by an automorphism. So the orbit of a tuple is defined by a conjunction of delta zero formulas that it satisfies with these particular delta n definable parameters, these AKs. Therefore, the orbit is defined by a conjunction of, this is actually a delta n statement in each case. So it's a infinitary pi n statement, and in particular, it's infinitary sigma n plus 1. Okay, so that's it. That's essentially it, as soon as you understand how automorphisms behave in such a structure J. For the general result, you now have a general model that came from a longer model A by taking the sigma n definables and closing downwards. So there you have to modify this criterion, this characterization of being in the same orbit to the following. Two tuples are in the same orbit if they agree on all delta zero formulas with parameters that are themselves parameter-free, definable by parameter-free Boolean combinations of sigma and -1 formulas. So you replace the set of parameters A0, A1, A2, A3 that you compare your tuples to by a somewhat more complicated set that is not likely to have type omega anymore in general. So you can't count on the standard cut being sigma definable anymore in general, but in such a model, which is the initial segment generated by sigma and definables, you will always have sigma definable cuts, arbitrarily small non-standard cuts. So you can go as low above n as you want and find a sigma and definable cut lower than that. And this suffices to sort of mimic the previous argument for that simple case with a sigma plus sigma and definable omega, but you need to do it with a small enough non-standard cut instead of the standard cut. And to find this small enough non-standard cut, you have to use overspill in the long structure, in the structure that you originally had that you took the sigma definables in. You have to use overspill in that structure for an appropriate formula. And there might be some annoying technicalities in case your first attempt to get a small enough non-standard cut gives you a cut that's not closed under exp. So then you somehow have to make another, not very hard, but sort of annoying effort to deal with that, because the proof of the fact that in a B model there are lots of automorphisms is about maintaining as an inductive condition that two tuples, you're building a back and forth isomorphism, and you want these tuples to agree on all delta zero formulas with parameters from a certain initial segment, and that initial segment should be closed under X because you're decreasing exponentially or even doubly exponentially the amount of parameters that the tuples agree on. Okay, so that's more or less how the lower bound works the upper bound works for the B model case. And now for the lower bound. So this is how you prove that any model of B sigma n has Scott rank at least n plus 1. So again, we'll assume that we have the exponential function. We'll sketch an argument that works for a general number n. The case for n equals 1 is simpler, and the exp is not really needed. And we'll make an additional assumption, which is sort of strange. Perhaps you can tell me that it's not needed because all models have a certain property, but I couldn't figure this out. So we'll take a model of sigma n collection with the additional property that there are at least two non-standard elements, let's call them A and B, such that whatever automorphism of the structure you have, it can't take A above B. So the orbit of A must be contained in the interval from 0 up to B. And frankly, I don't know if there are any models that don't have this property. So I'm pretty sure that there are models of true arithmetic that don't have this property. Namely, you can map any non-standard element above any other non-standard element in a well-chosen model of true arithmetic. And I guess recursively saturated countable should be enough for that. And it's easy to show that any model of PA that doesn't have this property has to satisfy true arithmetic. And in general, if a model without this property satisfies a certain amount of induction, then it satisfies a significant amount of the true theory of the naturals. But it seems like not enough to completely rule out the existence of those weird models without this property. So for example, if you have a model of I sigma 1 with this property, then it must, without this property, meaning you can map non-standard models arbitrarily high, all non-standard model elements arbitrarily high, then such a model of I sigma 1 must satisfy pi 3 truth. But that doesn't give you B sigma 2, or not to mention I sigma 2 yet. So I don't know, maybe one of you knows right off the bat whether such models exist. It's just a curiosity that we came upon. So let's assume that we're not in such a weird model. There is some element, non-standard element A, that cannot be mapped by an automorphism above another non-standard element B. Okay? And we've got to prove that every automorphism orbit in our model of sigma n collection is that we're proving a lower bound. So we must prove that there is an automorphism orbit which requires at least a sigma n plus 1 infinitary definition, that you can't do it in sigma n in general. So let's assume the contrary. Let's assume that every automorphism orbit of every element C has an infinitary sigma n definition, okay? Now an infinitary sigma n formula is a disjunction of formulas of the form exists and then a conjunction of pi n minus 1 formulas. Since the orbit is supposedly defined by such a disjunction, it has to actually be definable by one of the disjuncts. So we may assume that the infinitary sigma n definition of the orbit of an element C exists Y and then some conjunction of pi n minus 1 formulas. Let's take a witness for this exists Y quantifier. Let's call it D. It might be above C, it might be below C, you never know, okay? And now let's take an element E somewhere low down here below our A that codes the pi n minus 1 type, and here I mean just the regular arithmetical pi n minus 1 type without the infinitary business, of the tuple CD. Okay, so C is the element whose orbit we're talking about. D is a witness for the definition of that orbit. And let's take an element that just defines, I only mean the standard part, that codes the standard part of the pi n minus 1 type of the pair CD. Okay? Now, there is, by the amount of induction that we have, there is a smallest pair, C0, D0, that has its pi n minus 1 type coded by the same element E. Okay, so there's some guys C0 and D0 here, and their pair has the same pi n minus 1 type as CD does. In fact, even a small non-standard part of the pi n minus 1 type is the same up to this E. Because C0, D0 is the smallest, if you count the quantifiers, you can realize that the pair C0, D0 is sigma n definable with this parameter E. And if the pair is, then each coordinate of the pair is also sigma n definable. So this C0 is sigma n definable with this parameter E, which is below A. This E can't be moved arbitrarily high by an automorphism. We'll come back to that in a moment. And now here comes the connection between infinitary and just arithmetical sigma n formulas. This is something that was proved in Patrick's master's thesis as well, and I'm calling it the Wełek-Szlufik lemma because it just has such a cute abbreviation It's particularly cute for non-Polish speakers, and there's still some non-Poles in this seminar, so I decided to tease them a little bit. So the Wełek-Szlufik lemma says the following. It's a hierarchical version of a more basic fact that Montalban and Rossegger proved. If you've got a model of I sigma m, and this is really about a certain amount of recursive saturation rather than the induction as such. If you've got a model of I sigma m for some m, then actually tuples that have the same arithmetical pi m type have the same infinitary pi m type. So by this Wełek-Szlufik lemma, these tuples CD and C0, D0, since they have the same arithmetical pi n minus 1 type, they also have the same infinitary pi n minus 1 type. So that means that the D0 witnesses that C0 satisfies this formula. This formula defined the automorphism orbit of C. So C0 satisfies that definition. So C is actually H of C0 for some automorphism H. I could have added an arrow that connects them. Okay, so it turns out that there is an automorphism taking C0 to D0 because C0 to C. C0 to C because C0 satisfies the definition of C's orbit. But that means that since C0 was definable, sigma n definable with the parameter E here, which is below A, then C, if C is H of C0 where H is our automorphism, C will be sigma n definable with parameter H of E. And H of E cannot be bigger than this B here, because if you take any element below A and you apply an automorphism to it, you have to land below B. And that means C was arbitrary. So that means that every single element of A is sigma n definable with a parameter below B. But that can't happen because that's a violation of the sigma and pigeonhole principle. And the sigma and pigeonhole principle is exactly B sigma n. So that's impossible. So under this modest simplifying assumption that you can't have automorphisms that take very, very small non-standard elements to very, very large non-standard elements, we've proved the lower bound. So just a comment on how you get rid of this assumption. This is actually it's a one simple trick kind of argument. Now it sounds like you're cheating, frankly. I mean, I feel dirty when I talk about this argument, but it seems to work. So if perchance your model has this extremely weird property that you can map arbitrarily small non-standard numbers to arbitrarily large non-standard numbers by automorphisms, just expand your model by an arbitrary non-standard element. So just add a constant for a non-standard element. Now, in this expansion, our assumption is trivially true. You can't map that particular element to anything else, so you can't map it arbitrarily high in particular. You can repeat the previous argument and show that the Scott rank of the expansion by the single element has to be at least n plus 1. But then there's another very simple general argument that tells you that if you take a model and you expand it by a finite tuple, then the Scott rank can only drop. Because if you have a definition of the orbit CA for an arbitrary C and your chosen parameter A in the original non-expanded structure, then substituting the constant for A for the second variable in that definition defines the orbit of the first element in the expanded structure. So this is really trivial stuff. And as a result, since the expansion has rank at least n plus 1, and the non-expanded structure can't have lower rank, it must have rank n plus 1 or more as well. So yeah, so that concludes the sketches of proofs of the three things. So sigma n collection implies Scott rank n+1, and you can have rank exactly n+1, either in a model of sigma n collection, not sigma n induction, or in a model of sigma n induction, not sigma n+1 collection, whichever you prefer. And in fact, the classical examples work. So here is some stuff that we're thinking about currently. So we wanted to understand what other Scott ranks models of fragments of arithmetic can have. So for example, we know now that an I model at any fixed level n of the arithmetical hierarchy, an I model may have any infinite rank, and we know that it can have lots of possible finite ranks. It's like a positive density set of finite ranks. We suspect that it can. But it's not a very strong suspicion. But I think it's plausible at least that models of I sigma n and not B sigma n+1 may have any finite ranks starting at n+1 as well. And we know that they may have any infinite ranks. Something that I found more interesting than studying the Scott ranks of individual models was what you can say about theories enforcing a certain lower bound on Scott rank. So clearly there is a completion of I sigma n and not B sigma n+1 that lets you have Scott rank exactly n+1. But can there be a completion still inconsistent with B sigma n+1? That's the interesting question. That enforces much higher Scott rank. And the answer is yes. There are going to be completions of sigma n induction, not sigma n+1 collection, that insist on their models having Scott rank at least omega. And again, there will be others that are okay with finite ranks, but they will require the finite rank to be arbitrarily, well, above a certain fixed finite number. We know similar things for B models as well. There's a small, simple thing that we proved about recursively saturated models. I think this was in the Montalban-Rossiger paper, or maybe it's just a trivial observation that for models of PA, it's always the Scott rank is exactly omega +1. We have a proof that you don't really need PA for that. That in general, it's enough to have delta zero induction. And things that we're wondering about, other than improving these results and maybe improving the infinitely many alphas to cofinally many alphas, or exactly all alphas above n+1. So here is a thing that I find very interesting. Is there a completion of I delta 0 plus exp such that all of its models have Scott rank at least omega +1? We know that it's not true for PA because PA has these pointwise definable models. We have lots of examples of completions that will have a model of Scott rank omega, but we're not able to rule out that there might be some pretty weird completion. I think it would have to imply that there is no smallest definable cut, for example, so that all of its models have Scott rank at least omega +1. And a small technical thing that I was personally annoyed in this upper bound result for segments generated by sigma n definables, namely what I proved is that if you take a big model A, then you take its sigma n definables, and you take the initial segment generated by them. That initial segment is shorter by A, assuming than A, strictly shorter, assuming that A satisfied enough induction. Then that thing will have Scott rank exactly n+1. But I really needed this original longer model A, the end extension, at one step of the argument. And I don't think it follows from any of these known end extension results that this proof will work for an arbitrary model of sigma n collection with cofinal sigma n definables. So that's a sort of curiosity that I'm interested in. So I think I stop here, and these are a few references. These are mostly things that contain proofs of the background results that I mentioned. And there is also a nice survey, nice recent survey on Scott rank and the more fine-grained notion of Scott complexity by Harrison Trainer. So I added that to the references as well. And that's it. Thanks a lot.
Okay, thank you, Leszek. Let's thank our speaker and find my little button there. Okay. And we can take questions. All right, I'll go. Can you go back a couple of slides? I'm trying to
Meaning
remember.
exactly a couple, meaning two, or no?
Yes, actually here. Something, yeah, sorry, I just didn't get to jot this down. Let me see.
So this is the one neat trick, or one simple trick argument.
Right. Yeah, this is very very nice.
This is really
Very
weird,
Yeah.
and it took me a while to figure this out. So we were actually stuck at getting rid of this assumption, but then we realized that you get rid of it by adding a constant.
Yeah, very simple. Very nice. Okay. Sorry, I just missed that. Anything else? No? Okay, let's thank Leszek again.
Thanks a
Well,
lot.
you know, maybe this is
Go
all
ahead,
kinds
Ron.
of questions come to mind, but I do know they're probably all easily answered. But you know, this is all about PA in the original language, and do things become significantly harder when you look at Redux, say, just to Pressburger on those structures?
I have not thought about Pressburger at all. Well, Redux to Pressburger will be recursively saturated, right? They will always
Right.
satisfy Pressburger, and they will be recursively saturated.
Right, they will have lots
On
and
the
lots of
other hand,
automorphism.
Pressburger has quantifier elimination, doesn't it?
Right. So they will have the same.
But it's quantifier elimination in the finite first order language.
Mhm.
So I would have to think. I suspect that the answer might turn out to be not so hard, but I'm not going to try to answer that online.
Right, no, I know, and that's why I was really reluctant to ask it online, because no, but you know, there's this whole Richard Kay with his students. They work on the sort of all those things about the automorphism groups of models of Pressburger that would be analogs of things that we know about models of PA, and they found out all kind of non-trivial problems doing that in the description of the automorphism groups and how they act on the model. So what seems simple from the beginning, I think, you know, they all have.
Oh, you're saying that it might turn out to be a complicated affair in the end.
I did, you know, but nowhere in these considerations comes the standard system. Standard system is not contributing to the complexity of the structure. No, I'm asking a question just for PA. It doesn't really matter what, you know, whether it's a smaller Scott set or larger. It's right for the Scott's rank.
Yeah, I guess so. Is there anything special about Scott ranks of pointwise definable models? I guess no, right?
No. The point was definable. They must include probably all the types to certain level of complexity, because they would be coded. But so there is, you know, there are uniquity to them.
You're asking about models of PA, right, or not?
No, right. Even in the case of PA,
So
one
for
would think
model,
that if you look at the complexity of the model, one would think that the larger the Scott set, the more complex the structure, because you can code into the Scott set all kind of complications. But
not really. So Scott rank doesn't capture this. So like a simple example is these recursively saturated models, right? You can essentially have any Scott set as your standard system.
No, right. I see
In
that
a
because
in a recursively saturated model, right? And they all have Scott rank exactly omega plus one.
Right.
So it's
so
a
the fact,
different kind of complexity, right?
right. So it's probably because this Scott rank is really very rough in a sense that you allow arbitrary conjunctions and disjunctions and not say computable ones or something.
Yes, yes. So this is, I think this matters in general, right? That people do study effective fragments of L omega 1 omega, but this is really about arbitrary ones.
What would something like the next like omega plus 2 look like? Something that is not a pointwise definable model. So pointwise definable models you said is omega, I think you said,
I
and
don't
then
have
omega
I
plus
don't have
1
a
is
I don't have a great understanding of this, but the thing is, what they do in the Montalban-Rossiger paper is that they know that linear orders can have arbitrary uh, can have arbitrary uh, uh, that have arbitrary Scott ranks. In particular, a linear order might have Scott rank exactly 2. And then you sort of by interpret a linear order, and by interpretation it has to be simple enough. It has to be in a loose sense computable or continuous, like infinitary delta 1. You by interpret, you find a model of arithmetic such that a linear order of Scott rank 2 is by interpretable with not the model of arithmetic itself, but something that they call the structural omega jump of the model of arithmetic. So that's a sort of structure where you will have predicates corresponding to the sigma undefinable sets for all n, and then that means that the structural omega jump will have rank exactly 2, and that implies that the original model had rank omega plus 2. But how readable, how easy to understand such a model is after you go through all these steps, taking the linear order, moving from that to the omega jump of the model of arithmetic, and reading off the model of arithmetic from that, I can't say how digestible that can be.
Yeah.
I would recommend looking at the original Montalban Rossiger proof. I had a look at that paper, but I didn't really read it in detail because all results that mattered for me were reproved by Mateusz and Patrick in the meantime by fragments of arithmetic techniques. So those linear orders sort of disappeared.
I see. This is probably, as far as I remember, that this is done like for the orders. The only technique that's known is really Geifman, this technique of minimal types that allow you to iterate.
Yes,
and
Geifman minimal types definitely appear there.
along the ordering. So I guess they're sort of effective enough to be able to do some computation analysis.
Yeah. I think that's the point. I think that's how effective in some sense the Geifman technique is. Yes.
Well, again, these are questions that aren't really related to your talk, but just I'm thinking about it now. What about finitely generated models of arithmetic? Would they like models generated by a single element? Would that be a single non-definable or undefinable element? So that would be something along the lines of. Would that be omega plus 1, or would that?
Yeah, so let me say this without answering your question very precisely, although I expect that precise answers might be available. So your model will not be omega by the result of Mateusz and Patrick. The proof of that involves the Ehrenfeucht lemma, by the way. That's a neat application of the Ehrenfeucht lemma. I'm pretty sure that Mateusz talked about it at some point.
Yeah, he did.
Right. And then if your model is pointwise definable from a single element, then what that means is that it will have parametrized Scott rank omega, meaning that it's a certain expansion by this particular element will have Scott rank omega.
Yeah.
And that gives you a pretty tight upper bound on the rank of a Scott sentence as well. So yeah, that's a possibly good example. I would have to check what the exact. Okay, so if every automorphism orbit is sigma omega definable, and that's true in this case, then there's going to be a sigma omega plus 2 Scott sentence. So that's pi omega thrust 3 in particular. So an upper bound on the Scott rank is going to be omega plus 2.
Mhm.
But whether it's plus 2 or plus 1 or can be both,
Right.
I don't know off the top of my head.
Yeah. That's interesting. Yeah, I'm just thinking because it seems omega is what the pointwise definable models, which I would consider very simple, and then omega plus 1 are recursively saturated models, which I would consider very complicated. So it's somewhat interesting.
Yeah, so
to compare
in
yeah.
this measure,
Mhm.
it's models that are neither, which are the complicated
Yeah,
ones. They're
yeah,
the weird models in some
yeah.
sense.
Right.
Well, but if you think
That's fun.
about it in terms of what you study, I mean, what sorts of models does a simple man like me study to prove some unprovability result? Well, very often they will be either pointwise definable or recursively saturated, because that's the ones that we kind of understand.
Or Geifmann's models that are also the third category, and those are linear
Okay.
orderings.
Yeah.
So
Okay.
Interesting.
right, but what's in between? It's a sort of mystery. There are lofty models that still are waiting to be studied.
Yes.
There is a series of papers of Schnell and Kaufman, not Kaufman, on lofty. The loftiness is this notion that's weaker than recursive saturation, but gives you models that are not finitely generated, and there's kind of an intricate theory of those models.
Does it make sense for fragments as well, or is it just for models of PA?
Well, no, it makes sense in general. You replace realizability of recursive types with sort of bounding the set of realizations. The model is C lofty. Think of a type that you want to realize. So the recursively saturated models, you have a single element that realizes it. But in a C lofty model, there will be a coded set of size C, such that all all sorts of the formulas in the type are sort of realized in that small set. That's
Okay.
loftiness. So
Okay, so the smaller the parameter, the
the
more
closer
saturated.
the closer you are to
So
saturation.
one lofty is recursively saturated or something like that. Okay.
Exactly.
Okay.
You did mention, excuse me, you did mention the result that the Scott spectrum can be any countable ordinal for models of PA. So how do they go about making a model with a high rank? How do they get high countable ordinals?
Yeah, so this is what I tried to explain, although the Geifman construction is involved there.
That's the guy fun stuff.
That Roman knows way better than I do.
Okay, just iterating.
You find an effective enough by interpretation between a linear order of the right rank and not the model of arithmetic as such, but its so-called structural omega jump. And that tells you that the jump has exactly rank alpha for an arbitrary ordinal alpha, and therefore the original model of arithmetic had rank omega plus alpha.
Any other questions or comments? Okay, so let's thank Leszek one more time.
Thanks.
Thank you. That was great.
Thanks.
Thank you. And this concludes our seminar for this semester, and we will likely restart sometime in February of 2025. So
and most likely at the same time. But if you have any suggestions that we can do it more efficiently, then we will accommodate any reasonable request.
Of course.
All right, and thank you all for participating.
Thank you.
Thanks very much.